Now it is. Okay.
Okay, thank you.
Thank you.
Okay. So we were saying that we have two degrees of indeterminacy. You have also seen with Professor Gentina that you can decide which kind of restraint you can downgrade, and but in order to make things easier, we can start just suggesting to remove all the possibilities to remove all the constraints that prevent rotation. So we basically downgrade the flattening sections into hinges. Okay? So the first step is understanding how many degrees of restraint do we have, or the indeterminacy do we have. Then we know how many restraints we have to downgrade, and then we change the structure. We will not solve this one, but we will solve another one. So possibly this one. With the load. Okay? But we have also to add the tube and the moment that are basically the bending moments that are provided by the original restraint. In this case, it is X1 and it is X2. So, from a theoretical viewpoint, is this structure the same as this one? Yes, no? Maybe? Maybe. Maybe no with the true answer. Because this is true, but we also have to add the two conditions, and these are the compatibility equations. Okay? So let's give a name to the nodes. We have node A, we have node B, we have node P. We just say that the rotation in the node A has to be equal to something, 0, okay? Because originally we have a compatibility section, so there was no possibility to rotate here. Here there is a possibility to rotate, both according to the rotation can be used by the external load and the static moment, but the rotation should be prevented. And the second one is P in C is equal to 0. So this structure plus these two equations make this structure the same as this one. So we can solve this one. The main difference from this is that we can solve this one using only equilibrium equation because it is statically determined, and we cannot do that with the linear structure. So the next thing to do, yes. The next thing to do is to apply the superposition principle. Okay? So step A, step B, and now step B. So what does the superposition principle say? It says that we can apply to a structure if the structure is linear, it is nothing. All a series of external actions and if they are independent. And if we sum up the contribution of each independent action or force or bending moment, the result is the same as applying them all together. So we can consider the first structure, and obviously we will use the statically determined one under the external load. So this is called structure 0. Now, you have seen that if we consider all this kind of action and structure, we can just use the flexibility coefficient. Because what is our purpose? Let's always remind what is our purpose. Our purpose is to solve this structure. So find the reactions at the base and here, and then to solve the structure, meaning finding the values of the bending moment, of axial force, and of shear force. This is our final goal. We cannot do it because the structure is statically redundant. How can we proceed? We just apply the force method. We downgrade some restraints. We impose some unknowns, and in this case there are many moments, and then we impose a compatibility equation. Now, if P is equal to 0, it means that the contribution of PA due to the external load Q plus PA is 1, we can call it PA1, plus PA2 has to be equal to 0. Okay, so we will just consider all the external loads independently. We can find the values of the rotation in this point, always the node A, induced by the external load Q, induced by the first static unknown and the second static unknown. The contribution of the G contribution basically provides 0 rotation. So we can restore the original restraint. If we add that here there was not a clamping section, but a clamping section and a known rotation, here it would be not be 0, but it would be equal to that unknown rotation. We are not just saying that everything is 0 because it has to be 0. Everything is here is 0 because we know that here we have a clamping section. The second compatibility equation says that, applying the superposition principle, that rotation in P due to the external load Q plus P in P1 plus P2 has to be equal to 0 because in the node C we had a clamping section as well. So our problem now is not how can we use these two equations, but how can we find these terms? Well, it's basically very easy because applying for example, the elastic line, we have seen that we are capable to infer the values of these rotations simply applying, because they are simply called the flexibility coefficient. Okay, we have seen that if we just use the elastic line for any kind of structure, we can find the values of the rotations and of displacement at any point of the structure. Now, we don't have to compute them from 0, from scratch every time, because there are tables that have the values of the flexibility coefficients, and Professor Gentile has already shown you some of them, the most important one. So let's focus about the structure 0, the one associated to external load Q. So our goal is understand what is the value of PQ, PAQ. Okay, we just write from scratch the structure, we apply the external load Q, and we just try to understand how this deforms. Obviously, there will be a bending of the beam according to induced by the external load Q. So we have rotation PA Q. Here we have clamping section. This point cannot move horizontally because we in principle state that the beams are rigid in the longitudinal direction. Okay, so this point cannot go right or left because this point, the point node A, is fixed, and this beam cannot elongate. So this the horizontal displacement of this point is 0. The vertical displacement of this point is 0 as well, because also the column is rigid along its longitudinal direction. So this point is not moving. It can rotate because there is a hinge, there always can be. So it allows an internal and mutual rotation between the beam and the column. So the column is not undergoing any external load. So there is no way, no reason for a formation of this column. So P is equal to 0 because this column is undeformed. Whereas PAQ is known if we go and look for the flexibility coefficient. In this case, it is this one. This is supported beam under the vertical distributed load we expect the same rotation at node A and node B. PA is equal to PP. Obviously, the first one is clockwise, and the second one is counterclockwise, so they are the same modulus, but the sign is different. And the value is equal to Q times L to the power of 3 over 24 iota. L obviously is the length of the beam. E and iota are respectively the length modulus of the material of the beam. So this depends on the material, and the iota is the moment of inertia of the section, and so it depends on the geometry of the beam. So just to say, the rotation will be higher if the load increases. It will be higher obviously than we expect. It will be higher if the length increases because the beam will be more flexible and less stiff. And it will be smaller if E or iota increases because it means that we are dealing with a stiffer material or a stiffer geometry. Okay, that's trivial. So we know this one. In this case, Q is the load, L is the dimension, so you don't have to change anything. And before, E iota. Okay. So far so good. Well, the second structure is here. The geometry is always the same. This time we are considering the effect of moment x1. So we have a moment x1 applied in node A and nothing else. So what do you expect? The beam, the beam will deform, obviously, and we will have a rotation in the node A in the counterclockwise direction. So, okay. According to this node, it cannot move, but it can rotate. So the deformed shape will be something like this. Again, we know P A1 because it is the same as, okay, we have a generic unit bending moment applied in the first section of the simply supported beam with length L and with material with given length modulus and the geometry that leads to a moment of inertia iota. Okay. This is the first and the last time I'm doing it in detail, so don't worry. But if you don't understand anything, please tell me. So the P in the node, in the first node, we can call it node A, node B. The A in this beam will be equal to 1, which is the value of the unit moment, times L over 3 iota, whereas rotation in the opposed cross section is not 1 times L over 3 iota, but over 6 iota. So it will be 1/2 of the first one. So we know the A1 because it is this one, but this time it's not applied. It's not multiplied 1 because the bending moment applied in the node 1 or node A is not 1, but is x1. So we just multiply this part, this coefficient, times x1. So it is x1 times L because we have L over 3 iota. Okay? And P P1 again is equal to 0. Because here we have the possibility to have a relative rotation between the beam and the column. And so there is no reason why this column should deform. So far so good? Too slow, too fast? Okay. Okay, the last one. So we have found PA1, PT1. Okay. We still need to find the other two values. So the structure is still the same. Forgive me if I don't write or the geometry every time, but it's just to save time. This time we have x1, x2, sorry, applied in the node C. So again, it is counterclockwise at any moment, so the rotation in the node C will be counterclockwise. In the node B, we will not have any displacement, so it will be still here. Same for the node A. Is equal to, anyone wants to get? here, so I have more room, is EQ times L over 3D iota. Because it is the same as this one, as this case. In this case, it is perfectly the same. So we are still considering the rotation in the mode where the moment is applied. Whereas P A Q is still equal to 0. Okay? Because this being is on the format. So we just sum up all these terms that we have already collected and we put all this stuff in these two equations. Three training questions also from the audience at home. Sorry, which one? No, PD. No, we never thought about PD. We are only dealing with PA and PT. We can also compute the value of the PD associated to the load Q and to X1 and to X2. But it's not our main purpose because it's not here. If in your work you find find the quest, find the values of rotation in node P, you can also directly write also the PDQ, PD1, PDQ, so that you already have all the coefficients. This one. Ah, okay, this one. Yeah, because I was changing. Okay, this can be misleading. I was considering another case. Okay, so this was just a reminder for you. Okay. Yeah, I should have. Okay, I could have neglected it, but we will use it in the next exercise. Okay, so you don't need it. So we write again these two equations, but substituting in PAQ, PA1, PAQ, and so on, all these coefficients. So we have Q, this is equation 1.
Professor, can you move the camera a little?
Yes. Yes, yes, yes. No. That's better, right?
Yes, thank you.
Sorry, I cannot turn on the lights. Okay, so we are stating now that P, the rotation is not A is equal to 0. PA Q is the first term. So it is Q times L to the power of 3 over 24 each iota. Then we have PA1. For now, I'm not writing the signs, just the modulus. So PA1 is X1 times L over 3 iota. And then we have PA2, which is 0. Okay. All these three terms summed up are 0. Now, what about the signs? The suggestion is to take the sign that is related to the static unknown that is acting in this node, but it is the same. You can choose one sign or the other. In this case, each one is going counterclockwise. So everybody can see each one is counterclockwise. So we'll assume that all the rotations in the counterclockwise direction are positive. But you can choose also the other direction. you only have to be consistent when you write each equation. So in the equation, this was that. The 0 plus, okay. The other one is clockwise, so it is minus. Minus q to the power of 3, equal to 0. Then the equation number 2, the second equation is PCQ plus PC1 plus PC2. And we have 0, 0, and the Q divided by L, 3 is iota equal to 0. Okay, so plus. So that's trivial. We find that x2 always has to be equal to 0. Well, x1, I will do all this stuff to avoid mistakes. Multiply times L over 3 iota. We take this on the right hand side, we change this sign. So it is Q L to the power of 3, 4 iota. Okay. So it is x1 equal to Q L 3 24 iota times 3 iota over 10. So we divide both them times this one. So E and E, iota and iota. 3 and 24, we get 8. And we end up with Q times L to the power of 2, 8. This is right. Okay, so the minus, like put this on the line. Okay. So this is the value of x1. And the value of x2 is 0. So we have just adopted the compatibility equation, and we have found the values of the two unknowns. Okay. At this point, we can draw the original structure one last time. And we substitute the value of this direction of the original node, so it is Q and the power of 2 over 8. Then we have here we have an intersection. So this intersection provides us a vertical reaction dA and an horizontal one, HA, both in the non-C, sorry. We have vertical and horizontal. This is A, this is B, this is C, this is Q, and let's do math. We want to find the values of the actions, the first equation, it will be equation number 3. a vertical reaction in vertical equilibrium, we will find both dA and dC. If we impose the horizontal equilibrium, we will have both HA and HC. So there is no way to solve the structure preventing finding only one unknown, but to impose local equilibrium. So, for example, if we impose the moment, the equilibrium of the rotation of all the forces with respect to node A, or not B, only of the beam AB, in this case, the horizontal reaction, the HA, has zero level arm, the only unknown is BA. So we consider only the node, the beam A. So we have the A times its level arm, which is L, in clockwise direction. Then we have the X1, the former X1 unknown, which is counterclockwise, and it's QL to the power of Q over A. And then we have the contribution of Q, which is a force which induces a counterclockwise rotation with respect to the node B. So again, minus P, the force is P times L, and its level arm is L over 2. All this stuff is equal to 0. So we can easily find that if A is, we put this stuff on the other side, it's Q times L multiplying 1 over 8 plus 1 over 2, which means 4 over 8. So 5, 8, 2 L. Okay, let's enable. Oh, because the room is going to be assigned to L. So, well, okay, the resolution of this exercise, I am uploading it this afternoon. We will see the second exercise the next week. Apologies. Yeah. If you have any questions. Here. Yes, because we just impose we are just to select one component, one reference. Okay. So if VA times L is positive, it means that we're taking positive all the rotation in the clockwise direction. And all the other ones are negative. Otherwise, you can select the opposite reference. It's just to be consistent in each equation. Okay. So here you put in this case it was clockwise, yes. Yes. Okay, the lesson is done. And see you next week.